Hello, doctor. We are Group C. This is.
Today, we are going to talk about the Maxwell relations, which is some of the more important relations that can be used in thermodynamics to ease the application of equations such as Gibbs and Helmholtz function. Here, modeling the dependence of the Gibbs and Helmholtz function that behave with varying temperature, pressure, and volume is fundamentally useful. But in order to do that, we need to use Maxwell relation to simplify the equation so that it's easy for us to apply our calculation in order to simplify the calculation for consoled Gibbs method, even internal energy and enthalpy. So for example of internal energy, as seen here, internal energy, the different internal energy can be defined as temperature times the difference in entropy minus the pressure times the difference in volume. So if you partially differentiate, if you do a total added differentiation, you will get this equation. Okay, different internal energy equal to partial differentiation of internal energy over entropy at the constant volume times the change in entropy plus the partial differentiation of internal energy over volume at the constant entropy times the change in volume. So as you can see here, this one will equal to temperature, while this value will equal to negative pressure, as seen here. Okay, so if you partially differentiate this one over dv, and you partially differentiate this one over ds at constant v, you will get this equation. So as you can see, both the left hand side is equal to each other. That means the right hand side the right hand side will be equal to each other, as you can see here. Okay, so it means that the partial differential of t over partial differentiation of v at the constant s equal to the negative of partial differential of pressure over entropy at the constant v. So the next part will be given to my teammate who will be discussing about enthalpy.
Hi, now I'm going to talk about the enthalpy, and this is the main equation for the enthalpy. We are going to expand it to get the dH equal T ds plus V dV. Then we will find this one, which is dH equal differentiation h over differentiation s constant s multiplied by ds plus differentiation h dp constant s dv. This one referred to the t and this one is referred to the v. And here as you see, it's referred to the t and this one is referred to the v. And here we find the du over ds constant v, and dh over ds constant p. Then we are going to combine both of them in one equation. So differentiation over differentiation p multiplied by dh over ds constant p constant s. And this one is equal d over ds multiplied dh over dv constant s. All of this one is constant. So then the dt over dp constant s equal dv over ds constant p.
The general equation for Gibbs free energy is G equals to H minus T, as H is stand for enthalpy, T stand for temperature, S stand for entropy. And then first we have to finding the differential form. That is dg equals to dh equals to minus with d dh, and then we get one equation dh minus tds minus sdt, and then we have to substitute the differential form of enthalpy. That is dg equals to tds plus vdp minus tdx minus sdt. So finally we get the equation of the partial differentiation V over T, P equals to negative S over P. F when we get the value of S and P, it must be negative. Okay, that's all for my part. Okay, so the general equation of Helmholtz free energy F is internal energy minus temperature times entropy. This is actually in the question given is A, but we have some typo. Okay, and then firstly we actually substitute the function of fxy into t and v, and then we find the differential form of this equation, and we got df equals to du minus dts equals to du minus tds minus s dt, and then we substitute the differential form of the internal energy, and we got the equation df. The answer is df minus tds minus pdv minus tds minus sdt, and then and when we simplify, we get df equals to negative p dv minus sdt, and finally we got the final answer, which is this equals to this. That's all from our group. Thank you.